viewers, welcome to CEC-UGC online lectures. In my last lecture on alkyl halides, we had discussed SN2 mechanism for substitution reactions. We know SN2 reactions are bimolecular nucleophilic substitution reactions in which the substrate as well as the nucleophile takes part in the rate determining step. It is a one-step reaction in which the bond formation between the nucleophile and the electrophilic carbon as well as bond cleavage between the electrophilic carbon and the leaving group takes place simultaneously. In today's lectures, we shall be discussing factors affecting SN2 reactions. As you already know, that it is a one-step reaction in which the nucleophile, the substrate and the leaving group are involved in the transition state. So, the structure of the substrate, the nature of the nucleophile, the nature of the leaving group, and the effect of the solvent on nucleophilicity will affect the rate of the reaction. In today's lecture, we shall be discussing the structure of the substrate as well as the nature of the leaving group in the effect on the rate of nucleophilic substitution reactions, that are SN2 reactions. The structure of an alkyl halide plays an important role in influencing the rate of the SN2 reaction, as in the rate determining step the substrate is taking part. It is essential that we should have a good substrate. And what are the characteristics of a good substrate? A good substrate, to be a good substrate for an SN2 reaction attacked by a nucleophile, a molecule must have an electrophilic carbon atom. Electrophilic carbon atom must not be too sterically hindered for a nucleophile to attack. And then it must also have a good leaving group. That means we should have an electrophilic carbon which should not be sterically hindered, and it should have a good leaving group. Then only a molecule will act as a good substrate in an SN2 mechanism. Now there is vast differences in the rates of reactions at which the different alkyl halides undergo SN2 reactions. Methyl halides react most rapidly, followed by most primary alkyl halides. Secondary alkyl halides are slower, and tertiary alkyl halides do not react at all. In this table, which is coming on your screens now, I have tried to explain the effect of substituents on the rate of SN2 reactions. As you can see in the table, we have taken isopropyl bromide as a standard, in which it has been given value 1 for the relative rate. And the rates of rest of the alkyl halides are represented in relation to isopropyl bromide. What we observe here, that methyl bromide is most reactive. That is, it is 1000 times more reactive as isopropyl bromide. Whereas another primary alkyl halide, which is N-butyl bromide, it is only 20 times as reactive as isopropyl bromide. Whereas secondary alkyl halide which is isobutyl bromide, is only 2 times as reactive as isopropyl bromide. And tertiary butyl bromide does not undergo nucleophilic substitution reactions as indicated by the relative value less than 0.001. Neopentyl bromide is a primary alkyl halide, but it also does not undergo nucleophilic substitution reactions. What could be the possible reason for this difference in reactivity? So if we look at the structures of the alkyl halides, we can conclude or we can say that all slow reacting compounds have one property in common. That is, the backside of the electrophilic carbon atom is crowded by the presence of bulky groups. Tertiary halides are more hindered than secondary halides, which are more hindered than primary ones. In an SN2 reaction, we know that the nucleophile approaches the electrophilic carbon at an angle of 180 degrees from the leaving group. That is, the nucleophile attacks the electrophilic carbon from the backside. Now, as the substitution at the electrophilic carbon, that is the carbon at which nucleophilic substitution reaction is taking place, it increases. Steric hindrance will also increase, and the rate of reaction will decrease. That is, as the number of alkyl groups on the electrophilic carbon will increase, the rate of reaction will decrease. The reason being that when the nucleophile approaches the backside of the electrophilic carbon atom, it must come within the bonding distance of the back lobe of the sp3 hybridized orbital of the carbon. And this would not be possible if the bulky groups are present there. So if there are 2 alkyl groups bonded to the carbon atom, the process is difficult. 3 alkyl groups make it impossible. Reason? The 3 alkyl groups of a tertiary alkyl halide make it impossible for the nucleophile to come within bonding distance of the tertiary carbon. So tertiary alkyl halides are unable to undergo SN2 reactions. Here I have shown you the ball and stick model and tried to explain this concept. So if we look into the structure of ethyl bromide, then the methyl group is small. Since it is small, there is less crowding at the backside, due to which the nucleophile can easily attack the electrophilic carbon. Whereas if we look into the structure of tertiary butyl bromide, then there is more crowding, which blocks the access to the backside attack of nucleophile on haloalkane. That is, here I have depicted again that nucleophile is trying to approach the electrophilic carbon, but methyl group is offering steric hindrance, as a result of which this reaction does not take place. Now if we look into the reaction coordinate diagrams for an SN2 reaction, what we find that if we compare the reaction of a methyl bromide with a sterically hindered secondary alkyl bromide, we find that the transition state for a sterically hindered alkyl halide is unstable. It's the energy of the transition state is also very high. Since the energy of the transition state is high, we will need more energy of activation to bring about this reaction. Hence, the reaction of a sterically hindered alkyl halide will be slower when compared to unhindered methyl bromide. The second point that we have to keep in mind is that the rate of SN2 reaction depends not only on the number of the alkyl groups attached to the carbon that is undergoing nucleophilic substitution reaction, but it also depends on the size of the alkyl groups. For example, if we compare the nucleophilic substitution reaction of ethyl bromide with propyl bromide, both of which are primary alkyl halides, we find ethyl bromide is more than twice as reactive in an SN2 reaction because the bulkier propyl group provides more steric hindrance to the backside attack. Even a bulky primary halide like neopentyl bromide, in which we have a bulky tertiary butyl group, does not undergo nucleophilic substitution by SN2 mechanism, because in primary alkyl halides, the increased branching at beta carbon retards the SN2 reaction. The relative rates show that it is the bulk of alkyl groups rather than an electronic effect that hinders the reactivity of bulky alkyl halides in the SN2 displacement. What we mean here is it is not the polarization of the carbon, that is how polar or how electronegative the attached halogen atom is. The other factor which is more important is that the carbon which is undergoing nucleophilic substitution reaction should be accessible to be attacked by a nucleophile. Let us see the effect of substituents on the stability of the transition state in SN2 reactions. For this, I have taken methyl halide and a tertiary halide which is sterically hindered. So if we take the case of a methyl halide, the hydrogen atoms will offer less resistance, that is less repulsion to the incoming nucleophile, because they just have one electron in their first orbital. As a result of which, the nucleophile will be able to approach the carbon and the energy of activation will be less. The energy of transition state will also be low and it will be more stable. Whereas when we talk of a sterically hindered tertiary alkyl halide, here the hydrogens have been replaced by bulky alkyl groups. And these bulky alkyl groups will offer greater steric hindrance to the incoming nucleophile, as a result of which the energy of the transition state will be high and it will be least stable. The energy of activation will also increase, thus the rate of reaction will be less. So now if we try to classify these alkyl halides towards nucleophilic substitution reactions on the basis of substitution at the nucleophilic electrophilic carbon, then what we find that if the carbon which is attached to the nucleophilic carbon is highly substituted, that is, it is branched, like in case of neopentyl halide, then it will not undergo SN2 reaction. Similarly, in case of tertiary alkyl halides, they will also not undergo SN2 reactions because three bulky alkyl groups are attached to electrophilic carbon, which will hinder the access of the nucleophile to electrophilic carbon. Whereas if we talk of primary alkyl halides, then in that case methyl halide is most reactive, followed by rest of the primary alkyl halides. Secondary alkyl halides will undergo nucleophilic substitution reactions, but at a slower rate. The second effect which will affect the rate of SN2 reactions is the nature of the leaving group. Leaving group is very important since it serves two purposes in the SN2 reaction. First, it polarizes the bond, making the carbon atom electrophilic and more susceptible to nucleophilic attack. Second, it leaves with a pair of electrons that were once bonded to the electrophilic carbon atom. Therefore, what should be the characteristics of a good leaving group? A good leaving group should be electron withdrawing to polarize the CX bond. That is, it should withdraw electrons from this bond by -I effect, as a result of which carbon will have a partial positive charge and it will be susceptible to nucleophilic attack. When it leaves or when it departs from the substrate, it should depart as a stable species, that is, it should depart as a weak base. And the third, it should be polarizable. Because it is polarizable, then only it will stabilize the transition state and facilitate the SN2 reaction. So let us discuss these points one by one. As I've said, the leaving group must be electron withdrawing. So if the leaving group is electron withdrawing, it will create a partial positive charge on the carbon atom, making this carbon electrophilic in nature. An electron withdrawing leaving group also stabilizes the negatively charged transition state by making a bond at a longer distance. Now we know halogen atoms are strongly electronegative, so alkyl halides are common substrates in SN2 reactions. Alkyl sulfates and sulfonates are also good substrates for SN2 reactions. The second point is, which is again very important, that the leaving group must be stable once it has left with the pair of electrons that were once bonded to the carbon. That means it should leave as a weak base. We need a stable leaving group because stable leaving group will be favorable for the energetics of the reaction. As the leaving group leaves in the transition state, a reactive leaving group would raise the energy of transition state, thereby slowing the reaction. What we mean here is that the bond dissociation energy of this bond should be less. That is, since the bond length between carbon and iodine is large, therefore its bond dissociation energy will be low and it will easily depart from the substrate. Second, it is also a weak base, so this will facilitate the reaction. The next point that we have to keep in mind is that a reactive leaving group would raise the energy of the products, thereby driving the equilibrium towards the reactants. That is, if the leaving group is a strong base, it will drive the reaction in the reverse reverse. That is, the formation of the reactants will be favored over the products. Here I have shown again a reaction in which we see that the nucleophile is attacking the carbon from the backside, and in the transition state a bond has been partially formed between the nucleophile and the carbon, whereas at the same time the bond cleavage is taking place between the carbon and the halogen atom. Second thing what we find here is that the transition state is stable since the negative charge is spread over the nucleophile as well as the halogen atom. Now when this halogen atom departs, it departs with the bonding pair of electrons, and the halide anion which is formed is stable since it can accommodate the negative charge or the non-bonding pair of electrons with which it has departed from the substrate. That means halogens are good leaving groups. The next point that we have to keep in mind is that the good leaving groups should be weak bases. Therefore, they should be conjugate bases of strong acids. And if we consider example of halogens, then what we find that they are weak conjugate bases of strong hydrohalous acids. For example, chloride, bromide and iodide are conjugate bases of hydrochloric acid, hydrobromic acid and hydroiodic acid respectively. Other weak bases which can also act as good leaving groups are sulfonate ions, sulfate ions and phosphate ions, since they are also conjugate bases of strong acids, that is sulfonic acid, sulfuric acid and phosphoric acid. On the other hand, hydroxide ions and alkyl oxide ions are very strong bases, hence they are poor leaving groups for SN2 reactions. For example, the OH group of an alcohol is a poor leaving group because it would then leave as an hydroxide ion. These reactions I have discussed in detail while we were discussing the preparation of alkyl halides from alcohols. And there we found that since OH is a bad leaving group or a poor leaving group, we could not bring about the reaction when we treated methanol or any primary alcohol with sodium bromide, because the bromide nucleophile could not replace the strong base which was the hydroxide ion. So that means the ions that are strong bases such as hydroxide ion, alkyl oxide ion or an amide ion, they will be strong bases, that is poor leaving groups, and these reactions are not possible. So how can we bring about these reactions? We have an option that we could convert these poor leaving groups into good leaving groups by carrying out the reactions in acidic medium. When we carry out the reaction in an acidic medium, the hydroxide ion will be converted into a neutral leaving group such as water. So a neutral molecule often serves as a leaving group from a positively charged species. If we carry out the reaction of alcohol in acidic medium, then the hydroxyl group is protonated and water then serves as a leaving group. So how have we modified the reaction? We brought about the reaction in presence of HBr. So when we do the reaction in presence of HBr, in the first step, which is the acid-base reaction, the oxygen acts as a Lewis base through the lone pair of electrons on it, and it reacts with the proton from HBr, resulting in the formation of protonated alcohol. Now, Br attacks the electrophilic carbon from the backside, pushing out water as a good leaving group. Hence, we can bring about this reaction. Some other neutral molecules that can act as good leaving groups are water, alcohol, tertiary amines, sulfides and phosphines. The third point that we have to keep in mind is that a good leaving group should be polarizable. That is, it should be able to maintain partial bonding with the carbon in the transition state. This bonding helps to stabilize the transition state and reduce the energy of activation. Polarizable leaving groups stabilize the transition state by engaging in more bonding at a longer distance. That is, here the bond length is more, hence the cleavage of this bond will be easy. Among alkyl halides having the same alkyl group, alkyl iodide is the most reactive, while alkyl fluoride is the least reactive substrate. Iodide ion is one of the most polarizable ions, therefore it is a good leaving group. In contrast, fluoride ion is small, hard ion and a poor leaving group in SN2 reactions. The fluoride ion is such a strong base that alkyl fluorides do not undergo SN2 reactions. Now the size of the iodide ion is large. It is bigger than the fluoride ion, as a result of which it is more polarizable. That is, the electron cloud can be easily distorted because the electrons which will be involved in bond formation are present in the fifth orbital or the fifth shell, which is the outermost shell. And this shell is further away from the nucleus, so there is less attraction between the nucleus and these electrons, and the electron cloud can be easily distorted. So it is both a good nucleophile as well as a good leaving group. In contrast, fluoride ion is a small, hard ion. That is, the size of the fluoride ion is small and the electrons which are present in the second outermost shell are involved in the will be involved in distortion or in the polarization. These electrons are held firmly by the nucleus and they cannot be distorted easily. Hence, fluoride is a poor leaving group. Fluoride is also more electronegative, as a result of which and its size is smaller, as a result of which the bond length between carbon and fluorine is less. Therefore, the bond dissociation energy will be high and it will be difficult to bring about or to cleave this bond. So, on the basis of the structure of the alkyl group, we can say that if the electrophilic carbon is highly substituted, like in case of tertiary alkyl halides, then these alkyl halides will not undergo SN2 reactions. And the second point that you have to keep in mind, that in spite of being primary, like neopentyl halide, if there is branching at the carbon which is next to the carbon where the nucleophile is attacking, then also the reaction will not be SN2. Whereas methyl halides are most reactive because of the less steric hindrance, followed by primary alkyl halides, and secondary alkyl halides will react slowly. On the basis of the halide anion, we see that if we are keeping the alkyl group same, then the order of reactivity will be alkyl iodides greater than alkyl bromides, greater than alkyl chlorides. In the next lecture, we shall be discussing the effect of nucleophile on the rate of reaction, as well as the effect of solvent on nucleophilicity. Thank you.